In this video, we're going to take a look at making a proper Hirth joint in Fusion 360. Hey everyone, this is Matt with Learn Everything About Design, and in the last video I talked about lofting to a point. Now, lofting to a point is a great option for making serrated washers and ultimately Hirth joints. Now, in that video, there were a couple of comments and questions about whether or not we can use this technique to make a true Hirth joint. And there are also some comments about using parameters to drive the design, both of which are very valid and awesome comments. I really appreciate it when people do comment on the videos and ask questions. So I wanted to do a follow-up, and this is not a video I had really planned to do, but I wanted to do a follow-up to talk about both of those things. So the fact that we can use parameters to drive the design, and the fact that we want to look at creating a true Hirth joint. Now, if you don't know what a Hirth joint is, it's go ahead and just do a Google search for it, and you can see that it's essentially the locking serrated washer design. So very similar to what we did in the previous video. Now, if you want to just go ahead and skip ahead, there's a link in the description of the video. You can download this data set, which already has all the formulas plugged into the change parameters. So if you want to talk a little bit more about that in this first section, we're going to go through and we're going to create those parameters. So once again, if you want to skip ahead, go ahead and download the data set, jump to the next section in the video. So if you're still here, a Hirth joint is going to be essentially the mathematical equivalent of this locking serrated washer, this gear pair that you can use to lock two aspects of a design together. Now, these are used all over the place in power transmission and general design. You can use these to create a very unique and high torque load connection between cylindrical parts. So I'm not going to go through all of the back-end math to make this happen. If you want to learn that aspect of it, then go ahead and do a search. There's plenty of resources out there. There are books. There are plenty of websites that talk about this. What we're going to do is we're going to talk about the equations that we need to set this up, and we're going to talk about how that relates to the lofting to a point. Now, in the previous video, what we did was we created a loft to a point for a very simplified version of this. Now, the way that we did that is still going to be true, but there is a little bit more that we have to do to get a true Hirth joint. So to get started, a new untitled document, we're going to go into change parameters, and we're going to begin building out the parameters that we need to make this happen. There are a lot of aspects of this, and again, I'm not going to go into great detail. Once we start to use the formulas in the sketches, hopefully it'll begin to make a little bit of sense. But there are a couple of user parameters that we're going to need that are just going to drive the basics of the design, and then there are a couple of formulas that we're going to need to work out. The first thing that I'm going to define is the OD, or the outside of whatever object we're creating. And just like the last example, I'm going to use 100 millimeters. It's a nice round number. Then we need to determine the ID. In this case, I'm going to use 50 millimeters. Those were what we used last time. It's what we're going to use again. Now, I will say that in this video, I'm going to take a little bit of a different approach. Last time, we started with an extruded cylinder, essentially, and we cut away. In this case, what we're going to do is we're actually going to just build the tooth, and then we'll fill in the rest later. So the next thing that we're going to need is going to be what I'm going to call the Hirth angle. Now, a Hirth joint typically is going to be either 60 or 90 degrees. We need to make sure that we change the units to degrees, otherwise this isn't going to work. And for our example, we're going to use 60. Now, that's not to say that you can't use other angles, but everything out there for a Hirth joint is going to likely reference either 60 or 90 degrees. And that's going to be the angle of the triangle that we're going to draw. And once again, I'm calling it the Hirth angle because we're going to have formulas for the tooth angle and a projected tooth angle, and these are things that are going to come into play a little bit later. So the next thing that we're going to need that's a little bit different than what we did before is we're going to define planes based on these formulas rather than creating a sketch reference and doing a plane on a point. So for my OD, I'm going to call this OD plane. And this is going to be based on the outside diameter of our part. I'm going to divide it by 2 because the part is going to be centered about the origin. So anything we do is going to be a radius value. To make sure that I have a sketch profile that is outside of that, I'm just going to add 5 millimeters. Now, the 5 millimeters is just some random number. Obviously, you can have 1 millimeter, you can have anything you want. In reality, the OD plane doesn't really need to be offset that 5 millimeters, but it's good for us to make sure that our sketches are inside and outside of whatever solid we create. Just in the same sort of vein, we're going to do an ID plane. That's going to be the ID divided by 2. But this time we're going to subtract 5 millimeters. And this is because we want that inside plane to be set inside the inside diameter of our part. The next thing that we're going to define is going to be the number of teeth. And I'm just going to call this num of teeth. I like to use just capitals. You can also use an underscore. There's a bit of a limit to what we can do inside of the parameters in Fusion. So I just tend to use capitals. It's quicker for me to type that. We want to make sure that this is no units. When you see this pop up in a formula, it's UL or unitless. And it's important that we always kind of identify and understand these numbers and the fact that we don't have units when we're doing a number of instances in a pattern. I'm going to just set this at 20. Again, this is a value that can be adjusted later, just like the OD, the ID, the Hirth angle. The intention of doing a parameter-based design is to understand how each of these elements is going to affect the update. So making sure that we know that the ID and the OD values are going to control the location of the plane. Those planes are going to control the outside and inside profiles that we're going to loft between, and the number of teeth is going to affect the patterns. So now that we have the basis for the design elements that we are going to change, now we want to use formulas that are not going to change. Now, these formulas are going to be based on trig and some calculations that are based on general geometry for the Hirth joint. Now, once again, if you want to find this information, I suggest that you go ahead and do a search, find the references. If you just want to plug this stuff in, that's also perfectly fine. So I'm going to call this value the tooth angle. Now, when I say tooth angle, what we're looking at is going to be more related to like the root angle of a gear. And this is going to end up driving some of the geometry that we're going to need for the overall height of our profiles. So the tooth angle value just gets used later on in another formula that helps us determine the upper and lower portions of a tooth angle. Now, the reason that we're doing this is because we're driving the center position of the lofted profiles. And again, once we get into the sketches, hopefully this will all make sense. But this is going to be arctangent. So inside of Fusion parameters, we can do quite a bit with math operators. The only thing we don't really have is an if-else statement, which I've covered in previous videos with rounding using the ceiling and the floor operators. But in this case, we're doing the arctan. And in brackets, we're going to do the tangent, brackets again, 90 degrees. We have to put the DEG. The units of this parameter are in millimeters, so the result has to match that. This is going to be divided by the num of teeth. Now we're going to close those brackets. We're going to divide that by tangent, and that's going to be the tangent of 0.5 times the Hirth angle. Now the Hirth angle value, actually hit tab, the Hirth angle, and then we need to close it off with brackets. Now, if you ever have a formula like this that doesn't work, if it stays red, that means you likely typed something incorrectly somewhere. So you need to go back and you need to take a look at it. It says, please enter a valid expression. Now, the tooth angle is going to be in degrees because we're looking at a value that is in degrees, and that was the issue. Nothing was typed in properly. I had all the formula correct, but we have to, again, remember the units. And even though I gave that disclaimer at the beginning that we should check the units, I still missed it. But the good thing is that Fusion won't let you get it incorrect. If it wants degrees, if you're putting degrees into a formula, it's going to expect that value to be degrees. And it knows, even though it doesn't display degrees here, it does know what those units are. So now that we have this sort of tooth angle value, we also need to get a projected version of that. So once again, let's go ahead and change this to degrees. I'm going to call this one tooth angle projected for lack of better terms here. And we're going to go ahead, and this one is going to be arctan again. That's going to be brackets multiplied by tangent. And then we're looking at the tooth angle. The formula we just created, this is the value that we're using here. Then we're going to close those brackets, and we're going to divide this by the cosine, brackets 180 degrees, divided by the number of teeth. And all this stuff is case sensitive, so you need to get it correct. And we're going to say OK. So we can see that these values right now are 7.8 degrees and 7.9 degrees. And you might be thinking, these are really small numbers, or relatively close. Why does this matter? Why do we need to go through all this trouble? Well, when you're designing parts that are intended to be used in, let's say, powertrains, if you're actually designing a gear that's going to be in use, and I don't mean something that you're going to 3D print and is always going to stay as a 3D printed part. If you're actually designing something that is going to need to take a required amount of load, in this case torque on two opposing shafts, then you need to make sure that you do dive deep down into these formulas and make sure that you are following them in order to trust the calculations for how much torque value something like that can handle. So that's why we have to dive pretty deep down into using these values. Now that we've calculated the tooth angle and the tooth projected angle, and once again, so these are going to be the angle of the teeth based on the cylindrical surface that we're using. So it takes into account the number of teeth, which is 20 in this case, and it takes into account that Hirth angle, which is 60 degrees. And this result here is going to be used to calculate the overall height for the top and the bottom of our profiles. So next, we're going to create a couple of more parameters. We've only got 4 left, and that's why I said at the beginning of the video, you can download a data set that already has these values for you. But if you want to follow along, then just keep typing these in. So the next thing that we're going to create is we're going to create the inside profile, and this is going to be the bottom. Now, this will make sense again once we get into the sketch, but we're going to be using the ID plane, and we're going to multiply that times tangent. And inside of brackets for this inside profile bottom, we're going to use the tooth angle projected. We need to type all this in correct. We need to have all the brackets, and we're going to say OK. Next, we're going to create one called the inside profile top. And that, once again, is going to be our ID plane. And we're going to multiply that times tangent. But this time, we're just going to use the tooth angle. So what this is telling us here is essentially from the midpoint, because we are lofting from one profile to another, it's going to essentially tell us the amount of the triangle that's above the midpoint and the amount of triangle that's below the midpoint. They're relatively close numbers, but again, when you're talking about creating something that is actually intended to hold torque value or transmit force between components, in order to trust the formulas that are defining those things, you need to dive down this deep into them. So we're going to do the same thing for the outside profile, and spoiler alert, when we actually go to do this in practice, we didn't really even need the inside profile, and I'll explain why when we get to it. So for this one, we're going to do the outside profile top, and we're going to do the OD plane, and this is going to be multiplied by tangent, and the profile top is going to, again, use the tooth angle. And then we're going to do the same thing again for the outside profile bottom. So outside profile bottom, a lot of typing. Now, when I do this for myself, typically I shorten these. I think it's important that we understand. I'm not going to put comments in for everything, but I think it's important that at least as we're going through this in a video, we have names that are pretty representative of this. So again, we're going to use the OD plane here. We're going to multiply this times tangent, and we're going to be using the tooth angle projected. You can always click on these if you want. Tab doesn't work like it would if you were programming, but you can click on those. All right, and once again, we can see that the numbers are relatively close. They're a bit further apart than this one here, but this is essentially taking the center line path of the profile, and it's telling us how much of the triangle is above and how much is below. So now that we have all these values created, if you skipped that first part and you just downloaded the data set, then what we're going to do now is we're going to talk about the application of those. Now, in our last video, once again, we cut the tooth away. from the solid. In this case, we're going to build the tooth by itself. But in order to do that, I'm going to just create a sketch. This portion is not required, but what I want to do is I want to create a sketch just so that we can see the OD and the ID of the circle. This is going to be the size of washer or cylindrical feature that we ultimately make. And the reason that we're doing this is because we're going to use some of the values to create offset planes. And I just want to highlight their locations. So we're going to do an offset plane. I'm going to start to type in ID, and we're going to use the ID plane. We're going to right click to say OK, right click to repeat. Again, from the origin, from the default, it's going to be the default XZ plane. This is going to be our OD plane. Now, when we look at these planes from the top, what we should see is that the ID plane, in this case, is set in 5 millimeters from the inside of our solid, and the OD plane is set 5 millimeters outside of what will be our solid. So we're going to turn the origin off. We're going to hide that sketch, again, because it wasn't really needed. It was only there just as a visual reference. Now that we know that our ID and our OD planes are in the correct location, we can start building our profiles. So I'm going to start a new sketch. I'm going to select my ID plane. And one of the important things here is we are going to use the origin as our center. I'm going to draw a triangle. I'm going to move it over to the correct location, but I need to draw this in 2 different sections. And then I need to make sure that these lines are parallel or collinear. And then I also want to make sure that this center line here is construction. So I want to take this line and the origin and use my midpoint constraint, and then the vertical constraint from this upper edge here to that midpoint. The next thing that we need to do is we need to dimension the angle. In this case, this is going to be our Hirth angle, that's 60 degrees. So that's going to define the overall angle. And then we're going to go from that origin point to the top. And this is going to be our ID or inside profile top. And then we're going to do the same thing from there to the bottom. And that's going to be our inside profile bottom. So what we've essentially done is we have taken those formulas and we've used them based on our Hirth angle and based on the other parameters for our inside and our outside diameter, the number of teeth that we want. These are all the things that were used to calculate the tooth angle and the tooth angle projected. So we use these values to calculate where the upper and lower portions of that tooth would be. Now at this point, since we only have one profile, it doesn't make as much sense, but we're going to do the same thing on our outside plane. We're going to create a sketch. Using my line tool, once again, I'm just going to draw a triangle over here. You don't have to be real precise because we're going to use constraints, but it does help when you have the automatically applied horizontal constraint or parallel constraint. You do want to make sure that these are tangent, parallel, collinear, something that will make sure that they stay in line. And then we also want to make sure that this line here is construction. So we're going to do a midpoint between our construction line and the origin again. And then we want to make sure that we have a vertical constraint between that and this point here. Next, we need our Hirth angle to define that 60 degrees. So again, Hirth angle. Then we're going to go from our origin point to the top, and this is going to be our outside profile top. And then we'll do the same thing from that origin point to the bottom, and we can do our outside profile bottom. Now, once again, the important aspect here is that we're using these formulas to determine how much of the triangle is above or below that origin point. Now, you'll notice that I'm not calling it the midpoint because there is more triangle below that point than above it. So it's not its actual midpoint, and we could use that to get relatively close. If you're just 3D printing something and you're not actually looking to machine one of these joints, is it going to be close enough? Probably. In this case, we want to make sure that we do stick true to all the formulas. So what we have here at this point is going to be the inside and the outside, and we're going to loft between them. So we're just going to loft from here to here and say OK. And now we have a Hirth joint that is based on all of those calculations. Now, what I said earlier about not needing some of the information that we created, we didn't really need to worry about the inside because if we show our origin, everything that we did was based on the origin point. we calculated how much of this triangle was above and how much was below based on the location of that point relative to the origin. Now, this is why I always build stuff symmetric about the origin and use that as my reference point, because it simplifies the design and makes sure that you understand how everything updates. Now, if we look at the inside profile, once again, everything was based on that point. So it's the location that we have on our lofted profiles, and it actually happens to be the same location at the origin of our point, which means if we were to create a loft from here to a point, it's going to perfectly go through that triangle, that inside profile. Now, it might not be apparent there, but if we show the original solid body, those two are exactly the same. We have just stopped it short of this inside plane. So what that means is that as we're calculating these things, and as we're thinking about what constraints we need, we don't necessarily need to worry about the inside plane or the inside profile upper and lower portions of that triangle. As long as we're using that reference point on the outside, then theoretically it should still just be a loft to a point. We took a couple extra steps to make sure that we understood what those values were doing inside of the parameters. But once again, it's still essentially lofting to a point. We just happen to create a plane that's somewhere along that point. What that also means is that if you happen to know what that outside triangle is going to be, if you start a new sketch, and let's say we turn this into a 3D sketch, we go to Create, Project Include, and Include 3D Geometry. I'm going to grab the three outside edges of this, this extrusion that we have here. I'm going to right click and say OK. If I carry those lines to the origin, then once again, we'll be able to see exactly the same thing. Now, if I hide the solid body and I just show that last profile, we could do the same thing. We could carry those all the way down to the origin, and we would have all the information we needed as long as we know where that point is on the outside profile. We could still do a loft to a point, assuming that we have that point projected to whatever plane is at the center of rotation. So the key to this, the whole thing that this comes back to is understanding that the origin and the z-axis is the center of our rotation of our final design. If we don't have that center of rotation, then lofting to a point isn't going to work. But in our case, it does work, and we don't really need this last body, so I'm just going to delete it. But in our case, it does work because that's the reference point we used. Now, once again, could you get away with just lofting to a random point? In our example, what we ended up doing, our triangle was upside down, and we lofted to essentially the bottom point here, which is not a true Hirth joint. But once again, it wasn't intended to be. It was just looking at lofting to a point. So now that we have all of that out of the way, how do we turn this into an actual Hirth joint? Well, the next step for us is to create some revolves. Now, in order to do this, we need to think about a couple of things. I am going to do an intersection curve, project, include, intersect. I'm going to intersect with the bottom of this. The next thing that I want to do is I want to create the inside and the outside as a cylindrical representation. Now, if you remember the original sketch that we had, what we did was we created the ID and the OD in a sketch. The way that we could carry this on is we could use that sketch to intersect the solid body, or we could use a revolve to cut the solid body. It really doesn't matter which way you choose to do it. For example, if I make a sketch, I'm going to turn 3D off, and I use this dimension. This is going to be my OD, but this is my OD divided by 2 because I'm looking at a radius value. Then I could use this as a revolve. I could revolve this about my z-axis, and I could use it to cut the outside of that tooth. Now, I could do this with the profile on the inside as well, and all would be good. Or I can just simply take this. I can extrude it up and down. In this case, I'll do symmetric, and only keep what it intersects. So essentially, we took the ID and the OD, we cut the outside of that part as a sort of a cylindrical feature. Now, if I take this and I create a cylindrical, in this case, a circular pattern based on this feature, once again around my z-axis, the quantity is going to be my number of teeth. They should all perfectly line up. Now, you will notice that they're all individual solid bodies. They didn't combine because they actually intersect at a point or an edge. But essentially what we have is we've created a true Hirth joint. If we create two of these, if we just copy it, they should intersect perfectly, but we're not quite done yet. So the next thing that we need to do is we need to turn this into a solid body. So to do this, I'm going to go ahead and create a sketch. I'm going to use my intersect option. So I want to find the tooth that intersects that plane. Now it's important that we do use the tooth that we created, the original tooth. You can see here that I didn't, so I'm going to undo all of this. I want to make sure that I identify that original tooth. When I create a sketch, I want to make sure that I am bisecting that one. The reason that that's important is because if we decide to put a number of teeth that's odd, for example, we might not have the center of a tooth line up perfectly, or the tooth we select might not be in the section plane anymore. But if we stick with the original tooth that we know exactly where it was modeled, then we know that this intersection is always going to be there. And these are the kinds of things that we need to think about whenever we're talking about creating an object that has a parametric sort of condition to it. We want to make sure that we do update it properly. And I can just use all of these constraints. I can determine the overall height. I'm going to say that this is 25 millimeters. And then if I revolve this as a solid body, allow it to join, it should combine with all of the other solid bodies, and you can see we're left with just a single solid body. Now there is one last piece of this. Hirth joints don't typically go to a point. They'll have a flat on them, and we need to determine that flat because when we flip these things over, what we want is the side faces of the teeth to intersect with each other. We don't want them to intersect at the bottom of a point. So the way that we get around that is by really taking a look at how much gap we want. And once again, we can do this, find out where that original body was, and what we're going to do is we know that that upper edge is going to project itself down into the origin. So if I say intersect and I, let's see, pick that tooth, I should be able to find that point. And we know that if I draw a line from here down to the origin, that's going to be the top of that tooth. Now, so what I want to do is I want to take that and I'm going to offset it and just determine how much I want to cut off the teeth. I'm going to say 1 millimeter in this case. And I'm going to make the original one construction. I just hit X on the keyboard. You could also just do a revolve solid. So we could just finish this off as a rectangle. In this case, just use it as a revolve. Pick your axis and just cut the tops of all the teeth off. So now we have a single solid body. All of the teeth are built based on the geometry in the formulas. We could do a little bit more work. There's a little edge here. I don't necessarily like that edge, and it's just based on the differences in these angles. So that's something that we would want to work on and fill in. And that, again, that's sort of based on the fact that we the way in which we created this, we could do a revolve instead of the extrude and connect all those things. I'm not too worried about those final details at this point. If you followed along, you can finalize all that. But essentially what we want is we want to make sure that the teeth are all one solid body without any of those little gaps in it. Fusion's pretty good at healing some of that stuff, but in this instance, it looks like it did leave a little bit to be desired there. So at this point, the next thing to do would be to, well, first off, make sure that you save it. So I'm going to just call this my Hirth joint. And then you can play around with the formulas. Try to update it, see if everything changes okay. I'll be honest, I haven't actually tested this yet. This is the first time I've gone through and modeled it completely. If I increase the OD to 125, looks like everything is fine. If I increase the ID to 75, looks like everything is fine. We changed the Hirth joint from 60 degrees to 90 degrees. We can see that it did drop it down. And again, everything is parametric in nature. So that means if we modify any of these values, we go to an odd number of teeth, 25, looks fine. You will notice that There is a difference here. You can see that some of these teeth don't have the flat cut off of them. And part of that is because it didn't rejoin all of the teeth together. Now, sometimes what you find is you may need to go in and sort of recalculate this. Sometimes you can go to your utilities and compute all, and sometimes it'll fix those issues. Sometimes you'll actually need to go back into the revolve cut and make sure that it is cutting through everything, or back to this revolve and make sure that it is joining all the teeth together. Now, why that happens, I don't necessarily know. Sometimes it seems to calculate better than others. Of course, we could have done the geometry creation a little bit differently. We could have cut this away from the rest of a solid body as opposed to adding it onto a solid body. How you decide to make your own is really up to you. But in this case, I think we've proven that using the formulas to determine the Hirth angle and all of the different geometry is needed. And being able to manipulate the formula, in this case, we'll change it back to 60 degrees, make them a little bit steeper. And then if you have any issues, a lot of times what you want to do is just go back and rebuild that feature. Now, in this case, it gave me a warning because we went from 25 teeth down to 20, which means that it was missing 5 teeth it thought it was trying to join together. Just rebuilding the feature in most cases will allow that to work. If you have any questions on this, please let me know. Hopefully I covered the questions that came up from the last video on whether or not you can use this functionality to create a true Hirth joint. I think we answered that. If I didn't, please let me know. And also driving it based on parameters. So we have a design that we can manipulate a few variables, the ID, the OD, the number of pattern instances, the Hirth angle as I'm calling it, and have the design update. So pretty flexible design, does need a little bit more work to be complete in my mind. Again, I don't really like the interaction between the teeth and the base. Probably spend a little bit more time making sure that that's perfect. But other than that, I think overall the design works pretty well. If you have any questions, as always, please let me know. Thanks for watching, and we'll see you in the next one.